In this video, I'm going to continue the previous discussion on fiber reinforced composite materials. What are they? So this is part 2. Now we were speaking about plant fibers in the last video. And I mentioned that plant fibers were fibers extracted from plants. They are mainly cellulosic in nature. They are composed primarily of cellulose fibers, sometimes bound up together with a lignin matrix. Examples of such fibers include hemp, sisal, jute. I'm going to include plantain fibers and cotton. Starting with cotton, cotton is a very important plant fiber, very high percentage of cellulose, extremely high. It's important economically for many reasons. Explosives, clothing, a whole lot of very important strategic material. But I'm going to rule it out of the list because its properties are not suitable in general for use in composites. The properties are insufficient mechanical strength. These are the fibers on the list, as well as many others. We don't have enough time to go one by one talking about all of the details about every different type of fiber. But with these fibers here, their properties in general, one important thing to note about plant fibers is the fact that their mechanical properties, mainly tensile strength and modulus, generally fall short of what is required for certain high-end applications, unlike their synthetic counterparts like carbon fibers, glass fibers, etc. So their modulus numbers are significantly lower, very, very significantly lower. Their tensile strength numbers are also very significantly low. In general, for tensile strength, these plant fibers fall between 300 MPa to 700 MPa in the numbers, in the tensile strength numbers from mechanical tests carried out on these fibers. There's a lot of variation. The variation it depends on what species, the extraction method, whether the fibers were treated or not. There are a lot of reasons why that create lots of variation here. And it's a similar case with the modulus of the fibers, the modulus of elasticity or the stiffness of these materials. In general, they fall between 9 to 33 gigapascals. And by the way, these MPAs are megapascals for the tensile strength. The unit we're using for the modulus is gigapascals, okay? So in general, they fall between 9 to 33 gigapascals, and that is due to a bunch of reasons that also account for the variation in the tensile strength properties, such as the way it was extracted, what treatments were carried out, etc. But there's a lot of variation with plants, and that's one of the disadvantages also. With synthetic fibers, properties are more uniform, although there's variation with synthetic fibers as well, but there's greater uniformity, and you obtain that uniformity by very tightly controlling the production process and the conditions of production. And I'll talk about the production processes of some of these fibers as we move along. But with these natural fibers, one other important thing to note is that even though you have these numbers, there's a small exception to the rule with hemp in terms of the elastic modulus that its elastic modulus is very comparable to that of E-glass. E-glass has an elastic modulus of 72 to 76 GPa, but hemp comes very close at 70 gigapascals. So this is one little exception to that general rule that the properties don't quite match up. But on the tensile strength front, it does fall within this range. So that's also a limiting factor. And one way to keep these numbers in check is to understand that for synthetic fibers like fiberglass, well, we generally don't call it fiberglass. Fiberglass is a trade. It started as a trade name, but now it's kind of a street name. But the proper name is to talk about whether it's E-glass or C-glass or S-glass. E-glass means electrical glass. That has a good electrical conductivity, very low electrical conductivity, or it's a good insulator. For E-glass. With S-glass, S stands for structural, so that's glass fibers designed specifically, formulated specifically for structural applications. But it doesn't mean that E-glass or C-glass aren't used for structural applications, but the best mechanical properties are obtained with S-glass, structural glass, and it has a higher silicon content than the other types of glass that exist. The other type of glass is the C-glass, and C stands for chemical glass, just to very quickly run through that. So with synthetic fibers, examples of synthetic fibers, as I mentioned already, we have glass fibers, and they spread out into E-glass, C-glass, S-glass. You have carbon fibers. With carbon fibers, there are two major production processes that are used to produce these fibers, and their properties vary a little. So let me explain that. So as I was talking about the range for natural fibers, 300 megapascals to 700 megapascals in general, you're going to have small exceptions to this rule, but they usually don't go very far from these numbers. 300 megapascals to 700 megapascals for tensile strength. With E-glass, C-glass, and S-glass, they fall somewhere between 3,000 megapascals. So you can see the difference, 300 to 700. But here you have 3,000 MPa, megapascals. Structural glass can be up to 4,500 megapascals. The C-glass in general is somewhere closer to 3,000 MPa to 3,300 MPa, megapascals. E-glass is closer to 3,400 to 3,500 MPa. Okay. With carbon fibers, the properties are similar in terms of tensile strength. So carbon fibers range in strength from, the numbers range between 2,500 megapascals on the lower end to up to 7,000, which is amazing, MPa on the high end. Now in general, the polyacrylonitrile precursor, there is a precursor, a polymer precursor that is used in making carbon fibers, which is called polyacrylonitrile, PAN for short. So with the PAN fibers in general, they account for the lower end of these numbers. Whereas the coal tar precursor, there's a coal tar precursor which is used in making carbon fibers, they account for the higher end carbon fiber up to 7,000 megapascals. So coal tar. other important synthetic fibers, and I'm not going to talk about every single synthetic fiber, but I'll talk about the important ones, and then I'll then zero into the glass fibers because we will be doing a lot with glass, and I'll talk about the reason why. But I was talking about other fibers like Kevlar. Kevlar fibers are very important. They have, not only do they have good ultimate tensile strength of up to 3,000 megapascals as well. They fall in a similar range. Okay, they fall in a similar range, but the S glass edges out the average. The coal tar precursor, the carbon fiber made with the coal tar precursor accounts for the highest end of the spectrum so far. So with for tensile strength, it falls between somewhere in that range of 3,000 megapascals. For aramid fibers, which is another type of synthetic fiber, you have a result of a similar result also in that same range of 3,000 megapascals. Very close in that range. For modulus, the stiffness, carbon fibers rule the pack. So the highest modulus you have up to 260 GPa, gigapascals, for carbon fibers. For E-glass fibers, you have up to 72, I think I mentioned this before, 72 GPa, gigapascals. For S-glass, you can have up to 89 gigapascals for the stiffness. So you can see that these are very impressive materials. With S-glass in particular, you have not only a very high stiffness, you also have a very high tensile strength. And it's not as expensive as carbon fibers. So a lot of high-end applications that could be done with glass fibers, S-glass in particular, people just go in and say, let's go with carbon fiber, not realizing that there are variants of glass that actually, have impressive numbers, but are very low cost, relatively speaking. So they're comparatively lower in cost, and that's a very big advantage, particularly if it's for a manufactured product. So aramid fibers have up to a stiffness of up to 131 GPa. Kevlar fibers are on the lower end, around 60 GPa for stiffness. So having looked at these numbers, synthetic fibers, obviously fibers that are made using synthetic material, the main process for making these fibers is by using something called a spinneret, basically drawing these fibers through very tiny pores. So for the glass, it has to be at high temperature because the glass needs to be molten in order to be treated in that way. For the carbon fibers, the precursors, either polyacrylonitrile or coal tar, are, soft. They are polymers that can be drawn in that way before they are then treated and carbonized properly through a very special process, high temperature process, and they wind out, they emerge at the end of the process as fibers. They start out as polyacrylonitrile fibers, and then having been subjected to many processing steps in that furnace-like system, it's a production line basically. It eventually arrives at the other end as carbon fibers. So these are the key details to have, in mind about these fibers. Now I talked about what fiber reinforced polymer composites were, and I'm going to very briefly talk about that again. So just to recap, fiber reinforced polymer composites are made when two materials are combined to form a third material. Usually the fibers are combined with a matrix material. So for a composite, you have a phase, a binder phase or the matrix, and then you have a fibrous phase, but it doesn't have to be in this particular way. So this is a randomly wound up fiber, and that takes me to something called fiber orientation. Now, the way that a fiber is oriented inside a composite material matters, and it affects the mechanical properties. In an ideal situation, the simplest situation possible, we can have a composite material with unidirectional fibers lined up in one direction. That's why it's called unidirectional. So let's assume a composite, a polymer composite is made with fibers very neatly aligned in one direction. You're going to have maximum strength in this direction, maximum tensile strength in this direction, which will be that strength or modulus, either the modulus or the strength, can be obtained by a simple relationship like this. Modulus of composite is given by modulus of matrix times the volume fraction, and I'll talk about what the volume fraction is, plus modulus of fiber and the volume fraction of fiber, Vm, volume fraction of matrix, volume fraction of fiber. So this is the modulus of the composite. If you want to estimate, you can do a back of the envelope calculation, and I often do this to know how much